Hello, and welcome to this Let's Talk Meshing webcast. Today, we're going to explore an approach that may help engineers incorporate high-fidelity, physics-based, multidisciplinary analysis such as computational fluid dynamics or finite element analysis into their workflows during the conceptual design phase of aircraft development. This approach couples OpenVSP's easy-to-use parametric aircraft geometry tool with Pointwise's automated meshing capabilities to more readily automate the process of obtaining a viscous anisotropic mesh from users' models created in OpenVSP. To begin, I want to first introduce OpenVSP for those who may be unfamiliar with this tool. OpenVSP is short for Open Vehicle Sketchpad, and it is a parametric aircraft geometry creation tool being actively developed at NASA Langley. They have pursued development of OpenVSP because a lot of the work in which they are engaged typically revolves around conceptual design of aircraft. The latest release, version 3.3.0, can be downloaded via their website at openvsp.org. Conventional aircraft design is separated into three distinct phases: conceptual design, preliminary design, and detailed design. Each phase is distinct in the varying level of detail explored in each respective phase. A lot of the activities that highlight conceptual design, the earliest of the three design phases, involve a lot of changes to the geometry definition in order to explore a broad design space. Designers will typically need to interact with their design model many times manually, as well as perhaps employ the use of optimization in order to quickly develop designs for comparison. As a result, it is important that the geometry definition be created and modified easily with a minimum number of parameters in ways that do not yield nonsensical results. Conceptual design is also where the least amount of information is available to engineers, making it even more difficult to specify many aspects of the geometry with a lot of detail. Traditional computer-aided design, or CAD, software packages have strengths that are beneficial in the preliminary or detailed design phases, but actually have little benefit or become hindrances during conceptual design. A number of these programs originated in the manufacturing world and are characterized by their high precision, extreme flexibility, and ability to easily represent machining operations. The outer mold line of a typical aircraft is not produced using many of the geometry creation processes available within CAD, and so it takes a highly skilled user to produce aircraft geometries using these tools. As a result, the learning curve for CAD tends to be steep. OpenVSP aims to address these and other conceptual design geometry requirements specifically. As I mentioned earlier, optimization is an important activity designers and engineers actively engage in during conceptual design. This typically involves carrying out physics-based, multidisciplinary experimental design or parametric trait studies. Often high-fidelity analysis tools, such as computational fluid dynamics or finite element analysis, are precluded from being used during these studies due to the time investment usually required. The time involved spent meshing each of the design changes to the geometry in these types of case studies can account for a significant portion of the total time required. With OpenVSP and Pointwise's automated meshing environment, Glyph, a lot of this overhead can be eliminated, making the time invested in CFD or FEA types of analysis during conceptual design worthwhile. Now that I have introduced what OpenVSP is for those who may be unfamiliar with this tool, and outlined the impetus for coupling OpenVSP with automated meshing in Pointwise, I wanted to proceed with an example. On OpenVSP's website, they host a database of user-generated models, which have been shared with the community at large called the VSP Hangar. From here, I've downloaded one of their generic transport aircraft models. Once downloaded, I can open this model in OpenVSP. From the File menu, select Open, which brings forward an Open Save dialog window where I can navigate my local file system to the generic transport model I downloaded and read it into OpenVSP. A couple of features that were recently added to OpenVSP were the ability to create blunt trailing edges, on the trailing edges of wings for example, as well as the ability to export an analytical or mathematical representation of the parametric model using collections of B-spline surfaces to a standard CAD file format referred to as a step file. Having a wing with a finite trailing edge is often preferable to one with a sharp trailing edge when creating an unstructured mesh using Pointwise's anisotropic tetrahedral extrusion or T-Rex feature. Not only is it more realistic, but during anisotropic tetrahedral extrusion, having two convex corners allows T-Rex to eliminate large volume ratios or skew cells, which may result if a sharp trailing edge were used instead. So before exporting this model, I'll go in and create these blunt trailing edges on the wing, horizontal tail, and vertical tail parts. I can do this quickly by selecting the corresponding part in the geometry browser, take the wing for example, which brings forward a separate geometry definition window for that part. In the airfoil tab of that window is a trailing edge closure section where I can define the thickness of the trailing edge in a couple of different ways. Here, I've selected a value of 1.5% of the local tip-to-chord ratio for the airfoil section at the wing's root. I can repeat this for each of the airfoil sections that make up the wing part. Once I've updated the model to include blunt trailing edges on all of these parts, then I'm ready to export the model to a step file that can be read into Pointwise. From the File menu, I select Export, select the Step option from the available list, ensure that the Split Surfaces option is enabled in the Step Options menu, provide a file name for the exported file, and click the Accept button to proceed with exporting the generic transport model. One last thing to note, the latest release of OpenVSP now adds support for exporting models into an IGES format, which provides an alternative analytic CAD file format that Pointwise can import natively. Now that I have my step file, I can import the generic transport model directly into Pointwise. In Pointwise, select Import Database from the File menu. This opens an OpenSave dialog window where I can navigate my local file system to where I just saved the step file. After selecting the file, Pointwise brings up an Import Database panel with a few options that control how the model will be imported. The defaults for these options are usually adequate, so I'm just going to click OK and continue with importing the model. I can turn my attention to a couple of geometry cleanup tasks. If I inspect the list panel in Pointwise, I notice that I have several models. Pointwise refers to collections of watertight B-spline surfaces as models. Ideally, I would like to have a single watertight model of my geometry prior to meshing. This is what we refer to as solid modeling at Pointwise. When I select a few of these models, I also discover that the surfaces aren't trimmed with one another. For example, the wing is composed of 6 or so individual models, and the wing itself protrudes through the fairing attached to the fuselage, which are both themselves composed of separate models. To begin creating a single watertight solid model, I'm first going to select all of my models and combine them into as few parts as initially possible. In Pointwise, I can either select the models from the list panel or the display window. Then, using the Assemble Models feature in Pointwise, I reduce the number of models to just 6. The surfaces that comprise these 6 models will need to be trimmed before they can be combined further. To demonstrate this, I'll select the wing model in the display window and then select Trim by Surfaces in the Edit menu. This opens the corresponding Trim by Surfaces panel. Next, I need to select the surface I want to use to trim the wing. In this case, that's the fairing part, so I'll select it. The default intersection tolerance is fine, but I'm only interested in keeping the surfaces outside of the intersection. So I'm going to uncheck the Keep Inside option before clicking Imprint to proceed with the Trim by Surfaces operation. Now the wing and the fairing have been trimmed with each other and can be combined together into a single model. Before I do that, though, I'm going to proceed with trimming the remaining surfaces. Once I have completed trimming these surfaces, I'm left with 7 separate models that I can then combine into one. The reason there is an additional model at this point is because the horizontal tail was split into 2 separate models when I trimmed the horizontal tail with the fuselage. To get a single watertight model, I can use the same procedure as before, selecting them from either the list panel or display window and using the Assemble Models operation. The Messages window in Pointwise reports that 7 model surfaces have been assembled into one model. I can also see that I have a single model database entity listed in the List panel. I can further verify that I only have a single watertight solid model by selecting the model and choosing Models from the Assemble submenu item of the parent Create menu. In the table shown in the Assemble Models panel, I should see that my model has 0 lamina boundaries or free edges. Once I've verified that my model is watertight, I'm going to leverage the model's symmetry to split the model along its center line in order to mesh only half of the model. Doing so will create a number of lamina boundaries along the model's center line. Thus, I've deferred removing half of the model until now so that I can more easily assure that my model was watertight. To do this, I create a constant y = 0 plane, and then trim the model as before using this plane to trim the model surfaces. Then I can select the half of the model I don't wish to mesh, and either delete those surfaces or put them in a separate layer within Pointwise to hide them. Lastly, I'm going to group the individual trimmed surfaces that compose my model, Pointwise refers to these as quilts, into the intended analytic surface representation that I will use for my physics-based analysis. I'm also going to give each quilt a unique name. Combining quilts proceeds in a similar fashion as the previous model assembly. Simply select the quilts you wish to combine and use the Assemble Quilts tool within Pointwise. In the List panel, double-clicking on a quilt's name allows me to edit the name given to that quilt. My model is now ready to be meshed. Let me pause here and make a few comments. All of these geometry cleanup tasks could have also been accomplished using Glyph, Pointwise's automated meshing environment. However, references to each of the unique surface names within the step file would need to be extracted and explicitly included in the Glyph script itself. For a model consisting of several surfaces, including these references could end up being a lot more tedious than performing these operations manually in Pointwise as I've shown. Doing so also helps decouple the Glyph script from any specific geometry definition. One subtle advantage that models created in OpenVSP inherit, as opposed to those generated using more conventional CAD packages, is that the geometry surfaces are comparatively clean. There isn't a whole lot of effort required to prepare the model for mesh generation suitable for CFD or FEA analysis. You typically aren't going to encounter models with detailed design elements, gaps between surfaces, missing surfaces, or other common geometry anomalies familiar to FEA or CFD practitioners. Alright, so I've mentioned Glyph a few times now. What is it exactly? Glyph is a Tcl library that is packaged with Pointwise and which provides users familiar with the Tcl scripting language a text-based, procedural, object-oriented interface to all of Pointwise's features. Glyph has often been used to automate specific repetitive tasks, develop specialized meshing applications, or extend Pointwise's functionality. The models created in OpenVSP are typically simple enough that Glyph can be used for meshing the entire configuration, which is exactly what I'm going to demonstrate next. So here's a look at the Glyph script written to create a viscous anisotropic mesh around this generic transport example. The script defines a number of user input parameters, including the input file name for the cleaned-up watertight model, some edge spacing lengths for initial anisotropic refinement steps, mesh quality criteria, typical T-Rex control parameters, and the specific CAE solver to be used. To run a Glyph script from within Pointwise, select Execute from the script menu and use the Open Save dialog window to select the Glyph script that you wish to run. The first thing the script does is create a database-constrained isotropic mesh on all of the surfaces using the initial user-specified surface average edge length. The connectors and domains created during this step are identified and assigned descriptive variable names based on the unique name given to each quilt. Identifying the connectors and domains that are created in this way enables them to be easily referenced later on as needed. Next, the script applies isotropic mesh refinement to regions in the mesh which we know will be sensitive to flow conditions, such as the wing, horizontal tail, and vertical tail surfaces. The mesh refinement step uses another user-defined parameter used in controlling what the average edge length should be in these regions. Following this, the connectors along the root, tip, and span of the wing, horizontal tail, and vertical tail are given geometric growth distributions, as opposed to the hyperbolic tangent distribution that is applied by default. In the user-defined parameters list, parameters for controlling the growth rate and aspect ratio of this geometric distribution are available. T-Rex is then invoked to extrude anisotropic cells to resolve areas of curvature at the wing, horizontal tail, and vertical tail leading and trailing edges. Anisotropic mesh refinement helps to accurately resolve surface curvature without having to use an excessive number of grid points, as is the case with isotropic refinement. Before the surface mesh is completed, unstructured domains along the trailing edges are replaced with structured domains that are then triangulated to help reduce any large area ratios in these regions of the mesh. The end spacing of connectors adjacent to the vertical tail are also updated to be consistent with the spacing changes made earlier when the growth distribution along the vertical tail leading and trailing edge connectors was applied. At this point, the anisotropic surface mesh of the model is complete, and the script next begins creating the far-field and symmetry domains. The geometric extent of the model is computed in order to determine the model's center. This reference point is used in conjunction with another user-defined parameter to generate a semicircular curve that is revolved around the aircraft's yaw axis to generate a surface of revolution. A database-constrained mesh is generated on this surface of revolution, and these newly created domains and connectors define the far-field boundaries. A symmetry domain is created using the edge connectors of the far-field domains along with the connectors lying along the generic transport's center line. An unstructured block is created from all of the domains created so far, and then a number of 3D T-Rex extrusion attributes are set, some of which are exposed in the user-defined parameter list. The script next applies the appropriate T-Rex wall and match boundary conditions to the model's surface domains and the symmetry domain, respectively. Then, the script begins with the 3D T-Rex extrusion to generate the volume mesh. For this model, the process takes about 5 minutes to complete, and once finished, the script reports on a few important mesh quality criteria by printing these quality criteria statistics for the completed volume mesh to Pointwise's messages window. Finally, the appropriate boundary conditions are applied for the user-defined CAE solver, and the resulting mesh is saved as a separate Pointwise project file in the working directory from where the Glyph script was originally executed. Now, here's an important point about this process. If the underlying geometric definition were to change, but the assigned quilt names associated with that surface remain the same, then the script can be reused as written across any number of localized changes to the geometry. This means if I'm creating changes to the surfaces themselves, then I can reuse this script as is. However, if, for example, the tail configuration changed to a V-tail or Y-tail configuration, or a canard was added, then I may need to update the script to accommodate those changes. However, for shape changes to any of the included quilts, the script can help quickly automate meshing during experimental design or parametric trait studies. We've reached the end of this webcast, and I want to thank you for being with us today. If you have any questions about this webcast, then please don't hesitate to post your questions to the YouTube comments section below, or send us your questions to letstalk@pointwise.com. You can also tweet your questions to Pointwise using the Let's Talk Meshing hashtag.